Which regression metric should you use? Imagine you have obtained several models and now you want to choose which one is the best. Unfortunately, there isn't only one metric, only one statistical metric that you can use to say that this is better and the other is worse. There are several metrics which have importance for different cases. We will see a case study to see which metric is the best, and then we will present all the metrics, and we will also see some trap that can happen when you decide, when we will evaluate these metrics. So, two models, imagine you have two models to evaluate the price, to predict the price of 10 houses. Model A misses every single house by 10k, whereas Model B, it nails every house exactly, the first 9, and then a tremendous error of 100k on the last. Of course, the question is, which model is better? Model A, with its errors spread evenly across every house. Model B, 9 houses obtained exactly, only one large error. They are identical, okay, because 10 times 10 it's 100. And or it depends. Let's pick one before you continue to make this interesting. So let's go. So you have the same data, the same errors, but three verdicts. Model A, off by 10k on every house, mean absolute error 10k, root mean squared error also 10k, and this is the value of the mean squared error. Model B, 9 perfect predictions, 1 large miss. So, mean absolute error of 10k, root mean squared error of 31k, okay? So, 3 times larger the error, the root mean squared error for Model B. Mean squared error, way larger, okay? 10 times larger. So, mean absolute error says that two models are identical. The root mean squared error says that A is 3 times better. This model is 3 times better. And mean squared error, okay, model B is worse by 10 times. It's correct. It's useful for training, but measured in squared errors, which is not a unit we can easily visualize, okay. So, they have identical mean absolute errors and triple root mean squared errors. We will see what these errors, how these errors are calculated. Okay, this 3 times worse the root mean squared error. The metric you pick depends on the cost of having a large error. So your answer is it depends. Like most things in life. The three metrics. Now we'll look at the three metrics, see how they are calculated, and the advantages and disadvantages. First, mean squared error. Okay. The advantage is that it penalizes the large errors more heavily, which is the square of the error, making it more sensitive to outliers. Machine learning algorithms, they actually benefit from this penalization, which allows them to identify the global minima easily. So, we usually use mean squared error during model optimization, during the calculations themselves, the computations. Disadvantages: harder to interpret since it is not on the same units as the original data. It's the squared units. Mean absolute error. Okay, it's a simpler calculation. You sum the errors and then divide the number by the number of predictions. The advantages: it's simple to interpret. It's less affected by outliers. All individual errors are weighted equally in the average. If you had to say a disadvantage, it would be that the models does not take into account the direction of the error. Root mean squared error. it's the mean squared error, and then you just do the root, okay? The one that had no units, and then you do the root. This one right here. Advantages. Same units as the output. More straightforward to interpret than the mean squared error. Sensitive to outliers. Okay, this is an advantage. Disadvantage, also sensitive to outliers, since it is not something, if it's not something that you are concerned with. So it depends on the cost of outliers to your model. If it's an advantage or disadvantage to calculate, to use the root mean squared error. Just here the comparison, okay, mean absolute error, here the root mean squared error. Which should you use to optimize a model? Mean absolute error is less affected by outliers, whereas root mean squared error it's more affected by outliers. So if the cost associated with a large error is big, root mean squared error should be used. If the cost of the error does not increase significantly with the numeric value of this error, then you can use the mean absolute error. Just to review right here, root mean squared error, okay? You use when you have a large error, when the cost increases this faster than the error itself, okay? And you have to predict the outliers right. Mean absolute error, when you use when the cost grows in a straight line, the cost grows in a straight line with the value of the error itself. So in this case, the outliers will be noise and you don't need to predict them right. Okay. So both are in the same units as your target. You should report the two of them, but decide on only one. Usually, mean squared error you use to train the model, but not to report to a human since its units are just weird. Let's look into R squared and what it really means. Let's see that this is one metric that can move while your model and your errors can stay exactly the same. Let's see how. Because R squared is actually the most popular metric, and it's also one of the most problematic. Regression metrics. Let's go. R squared, it's calculated by this little formula right here. Basically, SSE, it means the sum squares of residual error, okay? The difference between where your output lies and the perfect value, according to your model, or according to the value that it should have, that is on the real value on the test set. This will be your prediction, and the real value will be right here. And this one right here, it's basically the spread of the epsilon. Okay, we'll see this in a while. The closer R squared is to 1, the better. Okay. Advantages. Intuitive quantification of the quality of the fit. You don't need to compare with other models to see if it's good or bad. Okay. When it appears 0.99999, for example, you know that you are on the right path. But does it tell it all? Let's see. Disadvantages. It can be close to 0 or close to 1 for good and bad models. Okay. For example, if you have a nonlinear model, we have all seen this, a nonlinear model, we can have an I R squared with a linear regression. Okay. The same function with the same mean squared error, but with a different epsilon range, can result in a lower R squared. Let's see what this means. Okay. Let's imagine this. Let's look at the R squared trap. Test set with a wide spread. The spread, it's this thing right here, okay, which depends on the test or validation set. This is the error on the formula, okay? And let's compare with a test set with a narrow spread. The same errors, but different spread. Okay, here a narrow spread, because on the R squared your errors are only half of that fraction. The other is the spread. Let's see what the spread does. Imagine this case where you have a large spread but the same errors as a smaller spread. The R squared would be like 0.9 and the R squared here will be 0.2. Okay, same slope, same residuals to the decimal, only the range of the test set changed. Okay, the R squared fell from 0.9 to 0.2 without anyone even touching the model. Okay, that's it. Here another visualization, same errors as in the case right here, but here a larger spread, okay, and R squared is way better. Identical residuals on both, only spread around the epsilon differs. Okay, if you see this professor right here, he has an interesting lecture about this. We will not go into this in detail, but about the R squared on this chapter 10, if it's a distraction or nuisance. And he had a small comment. He was responding on the notes of the lectures to a Reddit comment from one of his students, and he says right here, very interesting: "Greetings, Redditors. May I trouble you to read to the end before commenting? To Audiendi. I don't know who you are. I won't try to find out, and you wouldn't be in trouble if I did." This is a very good professor. And what does it say about the R squared? It says that, for example, unfortunately, a lot of myths about the R squared have become endemic in the scientific community, and it is vital at this point to immunize you against them. Just something that I highlighted. R squared cannot be compared across datasets. Again, look at the equation, we have to go above, and see that exactly the same model can have radically different R squared values on different data. Now we can read this one. The one situation where R squared can be compared is when different models are fit on the same data set with the same untransformed response variable. Then increasing R squared is the same as decreasing in sample mean squared error. In that case, however, you might as well just compare the mean squared errors. What is the problem with R squared? There isn't really a problem. The problem is that people started to only report R squares and not caring at mean absolute errors, mean squared errors, or root mean squared errors. And they attribute a little bit too much value, okay, to R squared. So be careful with that. How should you measure these metrics honestly, okay? A great score on your own data, your model, as already seen, is not a score at all. And in machine learning, a lot of people do this. So these metrics should be reported, especially for small data sets, using cross-validation. What is cross-validation? Is when you train on a part of the dataset and validate of the other, and you repeat this several times, always changing the validation set, okay? So you should choose your best model according to the validation set, and then when you have the truly best model, you test on unseen data that you reserved only to test at the end your very best model. Usually also reported in literature, I don't have here the article, but when your K it's equal to 5 or 10, it's usually enough to avoid bias to a particular part of the dataset. I usually report also 5-fold cross-validation and 10-fold cross-validation and see if the results don't change a lot, because here you evaluate more times, okay, sure, but you also have more information, because uh, 10 times will be you'll reserve 90% of your data set for the training, and here you'll just reserve 80%. But we can see that in the future. So when you make this decision after choosing mean absolute error or root mean squared error, make this decision in relation to the value of cross-validation. Okay, in that way you can have the final value but also the standard deviation of the value itself. Now the regression metric cheat sheet. So training, when do you use the mean squared error? When training and optimizing a model, okay, during the computations itself. Root mean squared error or mean absolute error when reporting a number to a human, okay. These are the easier to evaluate for the human to think about the error. Root mean squared error when big errors, large errors are disproportionately costly. And don't ever report R squared alone. Report R squared, okay, but never alone. Look at R squared and also root mean squared error and mean absolute error. So I don't mean that R squared is not important. What I mean is that you should not use only to evaluate. So you should optimize the model during the computations with mean squared error. You should report the mean absolute error, root mean squared error, and R squared, and make appropriate decisions considering the advantages and disadvantages that we mentioned for all of them. So here, the lesson here is, do not rely on only one performance metric. Thank you. If you have doubts, leave us a comment with a question, and let's go to the next video for the next topic.